Everything you know, every mountain, ocean, forest, and city, began as countless tiny rocks drifting around a newborn sun. In our previous explainer, we actually looked at the birth of our solar system, right? We watched as a swirling cloud of interstellar gas ignited to form the sun, and how those sweeping solar winds started to clear out the cosmic fog. But while the outer and inner planets were just sort of beginning to take shape from all that leftover debris, one specific, rapidly growing world was destined to become something, well, extraordinary. Welcome to the Cinematic Explainer. We're going to journey back in time to witness the violent, completely awe-inspiring origin story of our home planet. We'll watch Earth literally assemble itself from dust, survive catastrophic bombardments, and forge the very foundations of the ground you're standing on right now. It's an epic story of chaos, extreme heat, and just incredible cosmic forces aligning perfectly.
So, following the birth of our solar system, our future home was really nothing more than a chaotic, swirling debris disk of hydrogen, helium, and stardust left over from ancient supernovae. I mean, if you had a camera floating in space 4.5 billion years ago, you absolutely wouldn't see a beautiful blue marble. No way. You'd just see a massive, flat, rotating ring of cosmic grit and gas stretching for millions of miles. And yet, embedded within that hazy, chaotic ring were literally all the raw ingredients required to build an entire world. The process of turning that microscopic cosmic dust into a solid, structured planet is just one of the most fascinating mechanisms in all of physics, and it actually starts with the smallest of interactions.
Okay, let's dive into this process called runaway accretion. Think of accretion kind of like rolling a snowball down a hill, but, taking place in the vast, silent vacuum of space. Initially, the universe didn't even use gravity to stick these tiny dust grains together. Instead, it acted almost exactly like static electricity, bringing dust bunnies together under your bed. Seriously. These microscopic dust grains bumped into each other, fusing into tiny pebbles. Then, those pebbles violently collided to form massive boulders. As these boulders grew larger and larger, packing on millions of tons of material, they finally gained enough mass for gravity to completely take over the shell. These growing rocks became massive, kilometer-sized bodies called planetesimals. And once gravity firmly entered the equation, these planetesimals began sweeping through their orbital lanes like giant cosmic vacuum cleaners, smashing into one another and growing exponentially larger with every single impact.
By approximately 4.54 billion years ago, this relentless cosmic snowball effect had forged a massive, jagged, rocky mass that we call proto-Earth. And what's truly staggering here is the speed at which this happened. Geologic evidence suggests that the absolute bulk of our entire planet assembled itself in a mere 10 to 20 million years. I mean, in cosmic time, that is a literal blink of an eye. Recent scientific studies even suggest it could have happened in as little as 3 million years. But if you were to look at proto-Earth at this stage, you wouldn't recognize it as a planet at all. It wasn't a perfect sphere. Actually, it was this irregular, chaotic, lumpy amalgamation of rocks, heavy metals, and cosmic debris, just constantly being battered by relentless collisions from every direction.
But to become a true planet, this chaotic, jagged rock had to learn a completely new rule of physics as it grew ever more massive. And it brings up a brilliantly simple question that we honestly rarely stop to ask. Why are planets round? Think about it. Asteroids are shaped like bumpy potatoes, and small moons can look like lumpy walnuts. So what exactly forces a massive object like our early Earth to perfectly round itself out in the cold vacuum of space? Why didn't it just stay a jagged mountain of rock? Well, the answer lies in the sheer, overwhelming power of its own accumulating mass, and the inescapable inward pull that comes with it.
To really understand this, imagine the very center of the Earth as a deeply buried anchor point. As proto-Earth packed on more and more billions of tons of solid rock, the immense, crushing weight of gravity pulled equally from all directions toward that central anchor point. Eventually, the outward edges of the jagged rock just couldn't support their own weight anymore. The structural integrity of the stone simply gave way, shattering and collapsing under the immense pressure, forcing the newborn Earth to round out and collapse inward on itself. It became a perfect sphere because, well, a sphere is simply the most efficient shape for matter to gather around a single central point of gravity.
Now, within just 10 million years of its formation, the kinetic energy from endless, violent planetary collisions began to fundamentally alter the planet's chemistry. Every time a massive boulder or planetesimal slammed into the young Earth, the kinetic energy of its motion was instantly converted into extreme heat. Think about it this way. If you clap your hands together really quickly, you feel a tiny bit of warmth on your palms, right? Now imagine clapping two massive mountains of rock together at 30,000 miles per hour. The energy is so incredibly intense that the rock doesn't just shatter, it instantly vaporizes and melts into a liquid. Because early Earth was being pummeled relentlessly by massive space debris, it generated so much internal heat that the entire planet literally began to melt. It completely transitioned from a solid, lumpy rock into a glowing, spinning sphere of raging liquid magma.
This extreme heat triggered a major planetary event known as the Iron Catastrophe. Because the entire planet was now a fluid, deeply molten liquid, gravity was suddenly able to sort the planet's ingredients strictly by their density. It's exactly like shaking a bottle of heavy oil and water and then just watching them separate as they settle. The heavy, dense metals, primarily iron and nickel, were pulled forcefully down, melting and sinking straight through the magma to the very center of the planet. Meanwhile, the lighter, rocky materials called silicates were pushed upward to float on top. This massive, planet-wide internal migration of millions of tons of iron sinking to the core released even more immense heat, firmly locking Earth into a molten state for millions of years.
The aftermath of this iron catastrophe, a process scientists call planetary differentiation, created Earth's distinct layered structure that we actually still have today. Deep inside, we have the incredibly dense iron core at the center, surrounded by the thick, churning, rocky mantle, and eventually the thin outer crust on which we live. But that heavy, sinking iron did something miraculous for our long-term future. It gave birth to a rapidly spinning, liquid metallic outer core. The constant churning of this liquid iron acts exactly like a giant dynamo, generating a massive magnetic field that stretches far out into space all around the planet. And without this invisible magnetic force field, the brutal, highly radioactive solar winds from our sun would have completely stripped away any future atmosphere, leaving Earth completely dead and barren, just like Mars.
We now enter the Hadean Eon. This was a terrifying era spanning from Earth's initial formation to about 4 billion years ago. It's aptly named after Hades, the Greek god of the underworld, because, well, if you were to look at a cinematic rendering of Earth during this time, you'd see a literal, unmistakable hellscape. Earth was a glowing red, totally uninhabitable landscape covered entirely in deep, churning oceans of liquid magma. The sky above would have been this choking, dark, hazy mixture of outgassed volcanic vapors, heavy with suffocating water vapor, nitrogen, and carbon dioxide, but containing absolutely zero oxygen. Frequent, massive volcanic eruptions constantly tore the fragile, glowing surface apart, casting towering plumes of fire straight into the dark sky.
During the Hadean Eon, the early mantle was burning at least 1,600 degrees Celsius hotter than it does today. Because it was so incredibly hot, the heat flow from the deep interior to the outer surface was just massive. This drove a furious, highly accelerated version of plate tectonics. Convection currents in the deep magma churned at lightning speeds compared to what we see today. Thin, dark, brittle scabs of newly cooled rock would momentarily form on the surface of the glowing lava oceans, only to be instantly ripped apart by the currents below, swallowed back down into the terrifying depths, and melted all over again. Earth was desperately trying to cool off and form a solid outer shell, but the extreme internal heat simply wouldn't allow it to last.
Looking across the timeline of the first billion years of Earth's history really paints a picture of a planet constantly trying to cool, only to be repeatedly reset by absolute cosmic violence. Following its fiery formation 4.54 billion years ago and early desperate attempts at crust formation around 4.4 billion years ago, a temporary stability seemed almost possible. But just as the Earth's surface was finally beginning to solidify into a more permanent crust around 4.1 billion years ago, the cosmos unleashed a terrifying barrage. This entire era represents a world locked in a brutal, seemingly endless tug-of-war between the freezing cold of deep space, trying to solidify the surface, and the violent heat of the relentless solar system tearing it right back open.
Beginning around 4.1 billion years ago, a catastrophic era known as the Late Heavy Bombardment began. Deep in the outer solar system, the orbits of the giant planets were shifting, and in doing so, their immense gravity flung billions of comets and massive asteroids directly into the inner solar system. These gigantic, mountain-sized asteroids relentlessly struck the young Earth. The cinematic reality of this event is honestly hard to fathom. Imagine looking up at a hazy, choking red sky and seeing massive, glowing fireballs constantly breaking through the atmosphere, striking the oceans of magma and solidifying rock with the force of millions of nuclear weapons. This relentless bombardment completely destroyed the newly formed crusts, instantly boiled away any accumulating atmospheric progress, and kept the entire surface entirely sterilized.
Eventually, though,
As the solar system began to clear its orbital lanes of debris, the heavy bombardment slowed down. The molten surface, no longer being constantly obliterated by massive impacts, could finally radiate its immense heat out into the cold vacuum of space. Slowly, the vast lava oceans began to freeze into solid rock. This formed a dark, barren, basaltic crust, actually very similar to the tough volcanic rock that lines the bottom of our oceans today. As lighter minerals melted and floated toward the top over millions of years, the very first small, stable continental cores began to emerge from the darkness. These tough, incredibly buoyant masses of rock are known as cratons, and they basically act as the ancient anchors around which all of our modern continents would eventually grow.
Now, you might think a young planet made mostly of cooling lava and dark basalt would be completely, absolutely bone dry, but miraculously, scientists have discovered 4.4 billion-year-old microscopic detrital zircon crystals hidden in ancient rock formations. These nearly indestructible crystals act as the absolute oldest time capsules on our entire planet, and when carefully analyzed in a lab, their chemical signatures show clear, undeniable signs of contact with liquid water. This is an incredible revelation. It suggests that water vapor, delivered over eons by asteroid impacts and volcanic outgassing, was already raining down and beginning to pool into early oceans amidst the fiery, toxic landscape much, much earlier than we ever expected.
As the brutal Hadean eon finally drew to a close, Earth had taken the shape of a recognizable, stable planet. It had a solid, rocky crust, deep nascent oceans pooling in the craters, and a thick, heavy atmosphere. But make no mistake, it remained a completely inhospitable rock. The sky would have likely appeared a hazy, sickly orange thick with methane and carbon dioxide, kind of similar to what we see on Saturn's moon Titan today. There was absolutely no oxygen to breathe, no protective ozone layer to block the sun's lethal ultraviolet radiation, and absolutely no life of any kind. It was a silent, empty stage just waiting patiently for the next grand act in its planetary evolution. Just as the young world seemed to find its uneasy footing, finally cooling and stabilizing after tens of millions of years of chaotic accretion and terrifying bombardment, a massive, hidden danger was hurtling through the silent vacuum of space, heading right toward it. As the Earth spun peacefully with its new shallow oceans and dark, barren basaltic continents, it was completely unaware that it was sharing its orbital path with another massive planetary embryo. The peace was entirely an illusion.
Earth's greatest trial was only moments away. A rogue, Mars-sized planet, affectionately named Theia by modern astronomers, was on a direct, unavoidable collision course with our young world. This would be an apocalyptic impact that would literally vaporize the Earth's outer layers, completely reshape its future, and set the stage for one of the most magical features of our night sky. The sheer cinematic violence of this impending collision will forever alter Earth's destiny. But to witness the dramatic birth of the moon and the reshaping of our world, well, you'll have to join us in our next explainer. It leaves us with a really profound question to ponder. Could it be that the lush, living world we know today was only made possible by absolute apocalyptic destruction?